Now we've already done this for sine and cosine, but they're pretty important ones, so it's probably worth repeating again. We're asked to find, to derive the Maclaurin series for sine of x. So we can do that pretty easily. If we look at our function sine of x and we take repeated derivatives, we get a lot of the same sorts of things over and over again. We get, let's see, we're up to negative cosine of x. And then eventually, after we've hit all the different possibilities, we start over again. Right? And then we just keep on repeating. So I'll just go on to the fifth one, I guess, and stop there. We're going to do the Maclaurin series. That means that x equals 0. So if we evaluate these at x equals 0, we get 0. We get 1, because cosine of 0 is 1. We get back to 0, because sine of 0 is 0. This time we get negative 1. We get 0 again, and we get to 1. And we get the familiar oscillating behavior between 1 and negative 1 with zeros in between. So we can say that sine of x is equal to 0 plus 1 times x plus 0x squared plus a negative 1 over 3 factorial x cubed plus 0x to the fourth plus 1 over 5 factorial x to the fifth plus dot dot dot. And if we clean this up, we get that the sine of x equals 1x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And you probably noticed that we're just using the odd exponents. And it's alternating in sign. So we've got maybe a 7th degree term and a 9th degree term. If we're following this pattern, it becomes pretty easy to generate these guys. Now the trick is, how do we skip every other one? And I think we've seen this before. We know that we can start with n equals 0 and go to infinity. We can't tell in the summation, we can't tell it to just use the odd values of n. So instead, we use x raised to the 2n plus 1. And that way, if n equals 0, we get 2 times 0 plus 1. If n equals 1, we get 2 times 1 plus 1. If n equals 2, we get 2 times 2 plus 1, and that's going to give us 1, 3, 5, etc. We're also going to have that same exponent as the factorial denominator, and the only thing we're missing is that alternating bit. So that part alternates back and forth, starting with a positive, ending with a negative, or starting with a positive, so we're going to have raised to the n. All right? If we let n equal 0, then we get a positive first term. Now this is equal to the sine of x if we have an x value that causes this series to converge. If the series does not converge, then it doesn't converge to anything, but if it does converge, then it converges to sine of x. And in this case, again, you can double check with the ratio test. You can show that this thing does in fact converge for all real numbers. So this is another fantastic series to memorize. Now it says to take the derivative, instead of going through the same process that we just did for sine of x to do the same thing for cosine of x, it's asking us to take the derivative. So if we differentiate this equation, we know that on the left side we're going to get cosine of x, which is exactly what we're looking for. X is going to turn into 1. We've got 3x squared over 3 factorial. We've got 5x to the fourth over 5 factorial. We've got 7x to the sixth over 7 factorial. And that we got a 9x to the 8th over 9 factorial. And you'll notice that these guys all simplify pretty nicely. We've got an extra factor of 3 here. So we've got 1 over x squared over 2 factorial. An extra factor of 5 here. So we got x to the 4th over 4 factorial. We've got an extra factor of 7. And that pattern continues. So we can say that the cosine of x equals, well, let's see, we don't want to have that plus 1 anymore, do we? We just want to have x raised to the 2n and 2n factorial. We're just interested in the evens. We're still starting with a positive, so we want negative 2 to the n, or negative 1 to the n, as long as we start with n equals 0. And I mentioned this earlier, but remember that sine is an odd function, so that makes perfect sense that we're going to use x raised to the 1, x raised to the 3, x raised to the 5. We're only using odd exponents because sine is an odd function. Likewise, cosine is an even function, and we've got an x raised to the 0, so we've got an even 0, 2, 4, 6, 8. These are even exponents because cosine is an even function. Now, we could have, if we had chosen to, taken the derivative of the actual series in this form right here. Had we done this, if we had taken the derivative of that series, take a look at what might have happened instead. We could have gotten the cosine of x equals the sum from, well, I won't worry about the n equals 0 yet. Let's just see what happens here. The negative 1 raised to the n is just a constant, so that part doesn't matter. The 2n plus 1 factorial is a constant, so that doesn't matter. And we get a 2n plus 1 for the power rule comes out front, and then drop the exponent by 1, we get 2n. So yeah, this actually does end up taking us exactly back to here, because the n plus 1s cancel out. So these are two different important power series, Taylor series, Maclaurin series, that you definitely want to memorize, along with the third one, which we've already talked about, e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. So these are the big ones. You want to memorize these. Memorize these.